Hello wonderful person, this is Anton, and in today's video we're going to be taking a look at the Miller's Planet from the movie Interstellar. But specifically we're actually going to be discussing something I've talked about in the previous video, where if a planet actually moves fast enough, you can technically warm it up entirely through the so-called background radiation that's everywhere in the universe. Let me slow this down a little bit, explain it in more detail, and welcome to What the Math. So if you watched the movie called Interstellar, you may remember that in the movie there was a planet called the Miller's Planet that was actually orbiting around this supermassive black hole called Gargantua, and the time on that planet was slowed down dramatically. I actually had to look it up, and I discovered that the actual value for how much the time was slowed down was approximately 61,000 times. In other words, a single hour on the planet was equal to like 7 years, I believe, or something like that. So this implies that this particular planet is actually experiencing tremendous amounts of time dilation, but also other types of dilation, because it's essentially moving across the space at just a fraction of the speed of light. There's actually a way for us to calculate how much in terms of speed of light it moves, and there is quite a lot of calculators online, but I've used the one I've used previously, this one from a website called emc2explained.info, where if you plug in the values, you'll get this number, which is actually the percentage of the speed of light that the Miller's Planet was moving at. Alternatively, you can also just take 1 divided by 61,000, and you'll get this fraction, which can then be used along with the formula right here to try to calculate the fraction as well. But basically, the Miller's Planet was moving at 99.9999999986656% of the speed of light. It's quite a fraction, actually, but that's not really what we're here for. What we're trying to calculate is the following. Now, let me back away for a second. All right, first of all, you may already know that space is actually not as empty as it seems. As a matter of fact, even though there's a lot of darkness in space, even this darkness is actually permeated with what's known as the background radiation. I've talked about this concept previously, and I've actually made a video entirely about it, but essentially this is the leftover radiation from when the atoms started to appear, and basically right after the Big Bang, about 300,000 years afterwards, there was a lot of plasma that suddenly started to create various protons and neutrons, and this created a lot of radiation, a lot of photons. Those photons traveled for 13.8 billion years and have redshifted to the point where they're now at a specific frequency, and you can actually, if you have a powerful enough radio telescope, see and hear it pretty much everywhere from any part of the planet. This particular frequency can actually be found on Wikipedia, and it actually is approximately 282 gigahertz, or if you translate this into wavelength, about 1.063 millimeters. Now, I need to convert this. I actually need to convert it into nanometers, because that's actually the value we're going to be working with. We're going to be working with nanometers, as you'll see in a second. So this is how many nanometers the background radiation is. It's about 1,063,000. So on Miller's Planet, as it moves around the black hole, and as the black hole also warps space around it, the prograde side, basically the side that the planet moves toward, is going to be experiencing a lot of blue shifting. And this blue shifting will actually decrease the wavelength of the background radiation to the point where it might even become visible light. I made a video previously where I explained how you could potentially have a completely habitable planet if it moves at a specific speed around a black hole, where the background radiation actually turns it into visual light and infrared radiation, which can actually warm up the planet. But Miller's Planet moves a little bit faster than that. So I wanted to find out what radiation it actually creates. Alright, so let's do some math here, on very sort of simple math. We're going to use this part of the formula to try to discover what wavelength we're going to be getting if the planet moves at the speed of Miller's planet. This is the ratio of two wavelengths, and this ratio is equivalent to this number right here. So in other words, if you were to take the original wavelength and to then divide it by the new wavelength, you would get this. So basically now, if I multiply it by the wavelength in nanometers that we got from this here, what we'll get is essentially 17.43 approximately. That's in nanometers. So in other words, what this means is that for Miller's planet, as it moves across the space around Gargantua, so here we're gonna simulate this a little bit better, the actual wavelength that it's receiving from the background radiation, so basically from that side that it's moving toward, is now 17.42 nanometers. Now, you may not know what this is, so we need to actually go back to Google and find out what kind of radiation this is. If you know anything about visual light, visual light's wavelength is approximately 400 to 700 nanometers. So this is actually even more energetic and higher frequency and shorter wavelength than visual light. In other words, we're no longer going to be able to receive heat or warmth from this particular radiation, but we're going to be receiving what's known as the extreme ultraviolet radiation, also known as EUV. EUV is basically wavelength of 10 to about 124 nanometers. And it's very, very, very similar, or I guess on the border of what's known as the soft X-ray radiation, but not there yet. This right here, it has its own sort of field of study actually, and it's a very, very interesting radiation that normally is actually stopped. Now it actually does come off from our sun and does hit our planet, but it's stopped in the very, very upper atmosphere. It does influence our planet a lot, and some scientists even suggested that it actually has quite a big impact on climate. So there is quite a lot of questions that could be answered by studying this in a little bit more detail. We know that our sun produces quite a lot of EUV, and a lot of stars do produce EUV as well. But we also use this particular radiation for something else on the planet. If you look up extreme ultraviolet, you may actually discover what's known as extreme ultraviolet lithography. In short, what this represents is an entire field of these really, really complex machines that we use today to essentially produce very complex processors, very complex silicon-based devices. And basically, most of the really powerful computers today are made using extreme ultraviolet radiation. It's a very complex process, so I'm not going to go into too much detail, but we are going to focus on what else EUV might do to the actual atmosphere or the planet itself. So this particular ultraviolet light is actually right here on the border of ultraviolet and X-ray light, so it's extremely, extremely powerful, very damaging to life as well, but luckily it never really reaches the planet. But I guess that really doesn't answer the question of what Miller's planet could be experiencing based on all of these effects. So if Miller's planet was actually receiving mostly EUV light, basically extremely, extremely highly energetic UV light, it's very likely that its atmosphere would be extremely different from how it was portrayed in the movie. First of all, and I guess this is the more important part, because it'd be receiving so much more EUV light than our own planet Earth, it's more likely that it would be pretty much stripped entirely of upper layers of atmosphere, or at least that's kind of the hypothesis behind it. It's also possible that it would eventually start reaching the surface of Miller's planet, and because of that, it might even potentially strip the Miller's planet of water as well. Now, we do see water on the planet, so it's possible that that water was simply there because Miller's planet also has this unusual time dilation. But this doesn't change the fact that maybe with time Miller's planet would actually lose that water. But I guess another question is whether the astronauts on the approach to Miller's planet actually were in any hazard from this radiation. Well, it's not really X-rays, so it's not really that powerful. EUV is essentially very similar to ultraviolet light, but a little bit more powerful. So in that sense, the astronauts probably didn't receive any dangerous doses of radiation. But the planet itself, over time, especially if the humans were to settle on it, would most likely become extremely dangerous to live on, because having these doses of radiation for long periods of time, especially if it starts coming closer and closer to the surface as it's basically breaking down the atmosphere, would definitely become problematic. Well, that's kind of all I wanted to do in this video. I really just wanted to kind of do a little bit of math and discover what sort of radiation that Miller planets receive from the background radiation that we see everywhere in the universe. Now, in about 100 billion years, we actually won't really be able to ever see CBR again, because it's going to become so weak that it's going to be practically invisible. So future aliens, future humans, and people, I guess, or aliens or species in the future will not even know CBR ever existed, because it's just going to be gone. Anyway, that's really all I wanted to do in this video. Thank you so much for watching. I'll see you guys tomorrow. Come back tomorrow to watch another video and learn something else, and click that bell button to get notified about the next videos. I'll see you tomorrow. Space out, and as always, bye bye.